Hi, everybody. My name is Rihanna Smith, and I am a senior chemistry major at Westminster, and I'm a part of the instrumental analysis class with my classmates here, Harris and Jake, and we're going to talk to you about our spectrophotometer project.
In this project, we have to build a spectrophotometer out of everyday materials. Like in our case, we use Legos, but a spectrophotometer is an instrument in chemistry used to figure out how concentrated a sample is. So it does this by shooting a beam of light, diffracts the beam of light, creating a rainbow spectrum. The rainbow spectrum is then reflected onto the sample, and at different colors of that rainbow spectrum or wavelengths of light, the sample is measured on how much of the light it absorbed or did not absorb. And so judging by the color of your sample and the color of light it absorbed, you would then be able to tell how concentrated the sample is.
So for building the spectrophotometer, we have to make it to be a durable, reliable, accurate, and precise instrument that could be used out in the field and nothing's gonna break or fall apart.
I think it's good to think about, like, if you're in the chemistry labs and you see like the instrument room and you see like all the big crazy instruments,
yeah,
we're trying to build one of those except with like cardboard and Legos, which is because they're these like huge machines, these instruments that do all these fancy complicated things, and people have worked so hard on them and they're very expensive, but we're trying to like recreate that with cardboard and Legos. I keep going back to cardboard and Legos, but like
sub $500 project.
Right. Yeah, we have $20 max limit. Like, yeah, that's what we're trying to accomplish, which is a crazy task.
So we had to create a light source for the spectrophotometer. We used an LED light, which we used a breadboard where we connected two batteries to the breadboard and used a wire to connect one of the batteries to the light and used a resistor to regulate how much voltage got to the light.
In this spectrometer, we would then made the entrance slit, which was right after the light source. The entrance slit is made so that only a small amount of light can actually enter into the spectrophotometer. And that is so that the rest of the instrument doesn't get contaminated with these stray light beams. It's one focused beam of light. And then as we move towards the end of the spectrophotometer, we have to introduce an exit slit. The exit slit is there so that only, like very similar to the entrance slit, the exit slit's there so that only a certain amount of light can get through to the detector, and that we know each time what light is coming through.
So with the next part of our spectrophotometer then is we have the light coming from the slit is going towards this lens. And what this lens does is it focuses the light, right? Yeah, the lens focuses the light to get it as not blurry as possible, like as clear as possible. After our lens, then we have this diffraction grating, and it kind of just looks like this little, almost like a filter, kind of like saran wrap in cardboard. But what it really is, when you get really close to it, it's actually like this pattern of grooves and this grating, which is why it's a diffraction grating. And what it does is it allows light to kind of bounce and scatter off of it in a way that it will produce a spectrum in the visible light range. And so we're actually then able to see a rainbow coming from the white light. It's a little bit like how you would think of a prism. Like if you think of a prism and how white light shines through it, it creates this rainbow, but a diffraction grating works through a different process, which helps to scatter the light in different ways than a prism would. So that's kind of how you can think of that. And then from the diffraction grating, we have our spectrum, and we reflect that off of a couple different mirrors. And so that was a challenge in itself to figure out how to get the mirrors to work best and how to set those up.
Like Rihanna said, the main problem was getting these mirrors to be analytically correct, And so the two main things we were looking for were right after the diffraction grating, we looked to see if we were getting a really clear rainbow spectrum. which we were. So we added our rotating mirror to that part, connected it to the rainbow spectrum that we had found, and reflected the rainbow spectrum onto another surface. And again, checked to make sure that we were captivating that whole rainbow. And once we figured out that we had the rainbow in the right area, we added a stationary mirror to reflect the rainbow light over to our detector. And again, that was good. We got it, and we raised our detector. Everything matched up. And as soon as we had realized that the wavelength of the length of the separated light, or the rainbow, matched up with the distance from the detector, and we were getting individually each wavelength of light to look at the detector, we could move on to the next part, which is putting everything into the box and making sure it's still quantitatively correct. The separated light is filtered through this exit slit, like I said earlier, that allows us to regulate the amount of light and type of light that can get into our detector, and therefore make a more quantitative answer.
So the detector is on a breadboard that is pretty much the same setup as the LED light. The only difference is that a voltmeter is attached to it, to the detector, and it's going to read how many voltages is absorbed through or registered through the detector, and from there the volts will be converted into wavelength. So as the light enters through the exit slit, like Harris has said, it's going to focus the big beam of light into one small singular beam of light. And so that's going to pass through your cuvette that's holding your solution or sample, and the detector is going to pick up whether it's been absorbed or passes through.
During the construction of this spectrophotometer, we realized that we did not have enough space inside of our little cardboard box to fit everything. But it ended up benefiting us because we added the light source in its own little 6 by 12 inch box. And the light source being in its own box allowed us to focus the beam through the entrance slit. And doing that in its own separate box allowed us to contain all of that extra light from the light source.
When we created the box for the light source, we also contained the cardboard box within the we made an extension off the cardboard box and made an entire box around the cardboard, and created a light source box as well. Not only did that help regulate the excess light for the light source, but it also stabilized and made the entire spectrophotometer more durable. So when you pick it up, the cardboard box is not going to be shifting at all.
So come to the Environmental Symposium to see our spectrometer made out of Legos, cardboard, and wood.
We're going to be doing live demos at the face-to-face event, so if you're able to make it, then please come and we can show you the inner workings a little bit better, and we can show you how it actually functions, and you can test out your own solutions then.